So this is the first of two plenary sessions that we have today. In this session, we'll hear the ACM SIGecom Doctoral Dissertation Award talk and the Best Paper Award for EC. And then in the afternoon, we have a plenary session with Hal Varian and Jonathan Hall. So today's first speaker is Yannai Gonczarowski from Hebrew University of Jerusalem. He was recently a postdoc with Amos Fiat and Michal Feldman at Tel Aviv. And he'll be giving his doctoral dissertation award talk on aspects of complexity and simplicity in economic mechanisms. So take it away.
So thank you very much, Ramesh. So as Ramesh said, in my PhD, I worked on various aspects of complexity and simplicity in economic mechanisms. Today, I'm going to focus on revenue maximization as a case study for that. And I'd like to start with actually a self-conscious apology. So this broad audience is made on the one hand from people who are very far away from my work, and on the other hand from people who have been my teachers either directly or through their inspiring papers. So to the latter, I'd like to first thank and apologize for and ask for your patience while I give a background that includes many things that I learned from you. So let's start. Here's a question. How should a seller price the goods that she wishes to sell if she does not know how much the buyer would be willing to pay for them? So traditionally, auctions or selling pricing mechanisms have always been of manual scale. Even the biggest of auction houses employ enough expert appraisers to be able to go manually and separately dedicate time to each item sold and decide upon the optimal starting price for the auction or other parameters of the auction in order to maximize the revenue of the sale. And this is no longer true. Each of these products, when you enter them, a split-second auction is performed to decide which ads to show to you. And each of these auctions by itself is many times worth less than a cent, but overall, they're worth many billions of dollars. And this high frequency, together with the low worth of each auction by itself, make any manual intervention completely impracticable. This necessitates the deployment and the study of online economic mechanisms of unprecedented scale. And this community has asked for the past few years, do they scale and how do they scale? And we're going to talk a little bit about that. So classic economic analysis usually asks, what does the optimal mechanism look like? In this talk, optimal is always going to be revenue maximizing, except for in the last few slides. And after we understand what the optimal mechanism looks like, we can ask what real-life lessons can we learn from the form of this mechanism. And the problem is that even in very simple settings in which we need to auction or price even only two items, the answer to the question of the form of the mechanism is extremely complex, and it's very hard to learn any real-life lessons from its form. In computer science, in contrast, we often ask about the complexity of a solution to the problem and how does the complexity of the solution scale, how does the order of magnitude of the solution look like as a function of the number of items or the number of buyers and as they grow. And more specifically, we ask many times, is there an approximate solution that's much less complex than an exact solution? How does the complexity of the approximate solution scale? Once again, is a function of the number of items, the number of buyers, the quality of the approximation also. And in this talk, I'm going to talk about results for two leading and wildly different interpretations of the word complexity in these questions, a mechanism representation complexity and the machine learning complexity. So just to give a taste of the results that I'm going to talk about, all of them are going to be in canonical models. So for mechanism representation complexity, we're going to ask, can a finite mechanism representation complexity suffice for approximate revenue maximization when auctioning two items or any number of items? We're going to give a positive result to a fundamental open question raised by Sergio Hart and Noam Nissan, my great advisors. And once we have a positive result, that is finite mechanism representation complexity suffices, we're going to ask how does this finite complexity increase as a function of the number of items or of the desired approximation quality. And I'm going to tell you about upper and lower bounds that thoroughly map the trade-offs between simplicity and quality in this setting. And regarding machine learning complexity, this community has asked for the past 5-ish years, can approximately optimal auctions be designed without full knowledge of the market? but only with sample access to the market, learning the parameters of the auction from the samples. And I'm going to tell you about the first result on learning up to epsilon optimal auctions in a multi-item rather than a single item setting. So let's start with a model. We're going to have one single model throughout this talk. So we're going to have a single seller that has some items that she would like to sell, and she has no other use for these items. So if these items don't make her revenue, she may well throw them away. And there are a number of buyers. Each buyer is going to have a private value or valuation. That's the maximum price she's willing to pay for each item. And it need not be the same for any two pairs of buyers and items. So each buyer and each item could have a completely different valuation. Just for simplicity, each buyer's valuation is going to be additive. So her value for any subset of the items is going to be the sum of her values for the item in the subset. And we're going to work in a stylized model where for each buyer and each item, the seller is given a prior distribution from which the value of this buyer for this item is drawn. And throughout this talk, this distribution is going to be independent for the different buyers and the different items. And the seller will be able to choose and commit to any selling mechanism or auction, obviously having to take into account that the buyer can strategize and can opt out. And the buyer is going to make these decisions to maximize her expected utility, which is the value for the bought items minus the payment. And a decade-old fundamental question in mechanism design is how can the seller maximize her expected revenue, expected over the given distribution, of course, given the prior distributions over the buyer's values. So some background for one item, one possible mechanism, if I'm going to want to sell this clicker, is to say $6, take it or leave it. And if there's only one buyer, it's very easy to calculate and solve, given the distribution of the buyer's value, to solve for the optimal price that gives optimal expected revenue. But there are also many other possible mechanisms for a single buyer. For many buyers, you can think about multi-round mechanisms, selling lottery tickets, pay me $6 for a chance of 3/4 to win this clicker, I don't know, stuff like that. And there's a very beautiful theorem by Meyerson and Riley and Zeckhauser that says that if there's only one buyer, no other mechanism, however complex, multi-round lotteries, etc., can obtain higher revenue than posting the revenue maximizing price. And this was extended by Meyerson to a complete characterization of the optimal mechanism also for many buyers, as long as we have one item or what's slightly more generally known as one parameter. What happens beyond one item? So say that we have two items, and we're going to ask how can the seller maximize revenue from selling these two items. So it's very tempting to say, well, the distributions are independent, the valuation is additive, so everything should decompose, and we should optimally price each item separately, as Meyerson tells us to do. This turns out not to be the case for very, very simple distributions. I'm not going to do this exercise now. It turns out that the optimal mechanism may be different. For example, for this distribution, I have two items, this clicker and this adapter. Each of them will be worth $1 and $2 with probability half independently. But think about 1 million and 2 million just to make things interesting. And it turns out that the optimal mechanism is not to price each of them by itself for $1 or for $2, but rather than to tie a ribbon around the bundle of both of these and tell the buyer, Ramesh, either you take both of them for $3 or you take none of them. You can't take just one. So maybe optimally send the bundle of both items. Turns out that if we slightly tweak the distributions, well, it's actually better to price each of them separately. So maybe price separately or bundle, take the best of the two. Turns out that slightly another tweak of distribution, the best thing is to offer either one for $2 or both for a discount price of $3. So maybe I'm starting to grasp at straws here, post a price for each item and a price for the bundle. Turns out that with two items, unlike one item, you may have to offer lottery tickets. So the unique optimal, each of these is the unique optimal mechanism. So the unique optimal mechanism here is to offer lottery tickets, to offer the buyer either to take both items for $4 or to pay $2.50, get the first item for sure and the second item with probability 1/2. The buyer can always also opt out. So up to the buyer which of these offers to take. So maybe only a few lotteries. Turns out this is beautiful work by Kostis Daskalakis et al. Showing that for very nice distributions, don't let these beta notation scare you. These are just bounded distributions on 0, 1 with polynomial support with a polynomial density. we're going to have to offer infinitely many, actually a continuum of lotteries to extract the optimal revenue from the buyer. So let's talk about mechanism representation complexity. As we said, even for 2 items, the optimal mechanism may be extremely complex, offer infinitely many lotteries, etc., which raises the question of what revenue can we get using simpler mechanisms. And to answer this, we have to define the word simple first. So there are a few options to define what simple or complex means. First one is qualitative. You can disallow some features of the auction. You can only allow for separate selling or separate pricing. You can only allow for packaging into different bundles. You can ask to disallow lotteries. This is kind of an all or nothing approach. And each of such studied feature that we know of loses at least a constant factor of the revenue. And in this talk, we're going to be interested in losing only an epsilon of the revenue. So this approach is less appropriate. A more appropriate approach is a quantitative rather than a qualitative approach to limit a numeric complexity measure of the auction. So fix a complexity measure of auctions. This is going to be basically a function from auctions to numbers. And this number is going to be the complexity of the auction. And we can ask, okay, so that we limit ourselves to a certain complexity, how good of a revenue can we get? Or on the other hand, if we want very good revenue, how high does the complexity of the auction have to be so that we can be certain that we can get this revenue? And this is kind of a shades of gray approach. The words shades of gray is spelled like this to show you my LaTeX skills more than anything else. There have been a number of complexity measures floating around, either the number of options presented to the buyer, I kind of framed you for this till now, the length of the mechanism description in some given language or in any mechanism specification language, a lot of very interesting work on learning theoretic dimensionality. And in the first part of this talk, we're going to talk about the first measure, which is arguably the simplest one, the number of options presented to the buyer. So it was well known that if we have only a single buyer, we're going to have a single buyer for the next few slides. Any truthful mechanism for a single buyer, however complex, lotteries, multi-round, whatever, is equivalent to specifying a menu of possible probabilistic outcomes for the buyer to choose from. So here's a possible menu. So the first row in the menu, if you choose that, you're going to get the first item with probability 0, the second item with probability 1, and you're going to pay $3 for this. If you take a look at the third row, for example, you get the first item with probability 40%, the second item with probability 60%, and you're going to pay $10 for this. And there's always the option, the bottom option of paying nothing and getting nothing. And the number of entries in this menu, entries not entrees in this menu, is the menu size of the menu. This was formerly coined as a complexity measure by Hart and Nissan, but goes back to work by Brees, Chawla, Kleinberg, Weinberg, Dobzhinsky, Durmi, Vondrak, et cetera, et cetera. And we're going to talk about this measure of auction complexity. So Hart and Nissan, 2014, asked, is there a finite menu size C that depends only on parameters and an epsilon that suffices for attaining a 1 minus epsilon fraction of the optimal revenue when selling n items drawn from any given, I remind you, independent distributions? And so what are they asking here? If you tell me a number of items n and a desired approximation to the revenue epsilon, can I, based only on n and epsilon, commit to a menu size C, 1.5 billion, such that then whichever distributions you're going to tell me, I'll be able to give you a mechanism with menu size at most 1.5 billion that maximizes the expected revenue up to a factor of 1 minus epsilon. And for a special case of bounded support where you know the bounds, Hart and Nissan have shown that if you can make this menu size depend on the bounds, then yes, this is doable. Crucially, they need the upper bound to be less than infinity and the lower bound to be more than 0. It actually depends on the ratio between them and explodes as this ratio goes to infinity. So the challenge here really is that basically the only way we know of making small menus is to rounding the menu very carefully because you have to maintain incentive constraints to a discrete grid. And for a menu rounded to a discrete grid to be finite, the grid has to be bounded. If a discrete grid is unbounded, you're going to get a discrete menu. It's not going to be of finite size. That's not going to help you, and this is the major challenge here. And Hart and Nissan went on to show that for correlated distributions, this cannot be done. A finite menu size cannot guarantee any fraction of the optimal revenue. And the first result I'm going to tell you about today is a positive result to this question. This is from a paper with Moshe Babayov and Noam Nissan in Stock 17, where we show a positive answer. Indeed, we can remove the dependence on L and H. Such a finite menu size exists, even if we don't know the bounds and distributions, even for arbitrary unbounded distributions, however ugly. And this, of course, raises the next question: what is the rate of the uniform convergence of the revenue as the menu size grows? How fast must the menu size grow as a function of n and epsilon? Or in simpler words, how good can low complexity mechanisms be? How complex must high revenue mechanisms be? So let's very, very qualitatively plot the guaranteed revenue as a function of the menu size that can guarantee it. More specifically, let's plot the guaranteed fraction of the optimal revenue as a function of a very qualitative bucketing of the menu size. So when we started working on this, this was what was known. Infinite menu size would give you everything, of course. As we said, beautiful work by Daskalakis et al. Finite menu size cannot always give you optimal revenue. The exponential there is a corollary of a very general result of Babayov, Morlika, Lucier, and Weinberg, showing that from which you can conclude that exponential menu size can get you a constant fraction of the optimal revenue. So all of these were unknown. It was basically known that this very qualitative function lies between the upper and the lower dashed green lines. The first result I already told you about shows that finite menu size would give you 1 minus epsilon of the optimal revenue. And actually, you can set epsilon to be 1 over n. Finite menu size would also give you 1 minus 1 over n. And actually, we give a tighter bound than that. We show that even if you want 1 minus 1 over n approximation to the optimal revenue, exponential in n menu size would suffice. Another thing that we show is by reducing to this result of Babayov, Morlika, Lucier, and Weinberg that I told you about, is that a polynomial menu size would actually also guarantee to you a constant fraction of the optimal revenue. And on the flip side, we show that if you really want a 1 minus 1 over n approximation, if you really want the approximation to get better as the number of goods increases, you need exponential. An exponential menu size polynomial is not going to cut it. And there's an open question here, which I think is very interesting for whoever in the audience wants to work on this line of work. 99% of the optimal revenue, can you guarantee that using a menu size that's polynomial in n? I don't know. So this should always be compared with what happens with correlated goods. Nothing can be guaranteed unless you have an infinite menu size. So to sum up the results I've told you about so far, poly n would get you some fraction, exp n would get you approximation that improves as n grows, but this is only half of the picture. Instead of fixing epsilon and letting n go to infinity, you can fix n and let epsilon go to 0 and ask about the dependence of the menu size as a function of epsilon. So for one good, as I told you, Meyerson, Riley, and Zeckhauser, they tell us that a single menu entry, just a take it or leave it price, suffices for complete revenue extraction. So the interesting question is for arbitrarily fixed n, 2 goods, 13 goods, 7 goods, fix the number of goods. How does the menu size have to scale as epsilon goes to 0? So the results I've told you about so far, as well as previous results for bounded distributions, for fixed n, they give a menu size that's polynomial in 1 over epsilon, but there was no known lower bound for any fixed n. It was only known, this is a result of the analysis of the Daskalakis et al., that the menu size would tend to infinity as epsilon tends to 0, but was not known at which speed. Could have hypothetically been log star of log 1 over epsilon or something like that. Only thing that was known is little omega of 1. So the next result I'm going to tell you about, this is from a paper of mine in Stock 18, is a matching polynomial lower bound up to polynomial factors. So there exists a distribution f on 0, 1, and we're going to look at 2 items IID from this distribution, such that for every epsilon greater than 0, the revenue from this distribution IID from F2 items of any mechanism with menu size order of magnitude at most 1/4 root of epsilon is at least an epsilon less than that of the optimal mechanism for f star f. So if you're going to have a menu size that's less than 1/4 root of epsilon in magnitude, you won't be able to extract up to an epsilon. So this is the first menu size bound for fixed n uncoupled from epsilon, so not setting epsilon equals 1/n or epsilon equals some function of n in any auction setting, even beyond the multi-item setting. And the proof uses, I'm not going to be able to go into that, but it uses the optimal transfer duality framework of Daskalakis et al. Recently come out in Econometrica, really some of the most beautiful math I've ever seen, their framework. And this duality framework was meant to certify optimal mechanisms, and this result is the first that manages to make use of this duality framework to reason about approximately optimal mechanism, and it's also the only duality proof I know of that manages to use duality to give a lower bound on the complexity of mechanisms. So let's talk about machine learning complexity. So here's a seemingly unrelated question to machine learning complexity. What is the computational complexity of calculating or computing the optimal auction? Thinking about this a little bit, the answer is, well, that really depends on how you specify the underlying distributions, the prior distributions. Conceivably, just reading the input could take a very long time. So here's a follow-up question. Actually, come to think about it, to understand how the distribution is specified, how does the seller learn about the distribution? An economist would usually tell you, well, they've observed many past transactions, they conducted polls, they know the market very well. And computer scientists over the past few years have started to say, well, even if we accept the stylistic assumption that there's a true underlying distribution that you want to maximize for, the seller doesn't really know this distribution. If they've observed a lot of past transactions, conducted many polls, the seller only sees many samples from this distribution. And the question here is, can the seller make do with polynomially many samples with polynomially stylistically, meaning many but not too many? And the sample complexity is the number of samples required for learning a good enough auction. So just to contrast and compare, so far we've talked about Bayesian auction design. It's a decade-old paradigm. The mechanism designer is given a distribution for which the bidder valuations are drawn, and the goal is to find a truthful mechanism that maximizes the revenue in expectation over this distribution. Empirical auction design from the past 5 or so years, initiated by Cole and Roughgarden. The mechanism designer is given polynomially many samples from the distribution, and even so, the goal is to find a truthful mechanism that compares well to the optimal benchmark had you known the complete distribution. So there are samples from distribution, you're given the samples, you need to output a truthful mechanism that maximizes, we'll get to this asterisk in a second, the revenue and expectation over the real unknown distribution. This asterisk maximize, obviously, since you're given noisy data about the distribution, it's going to be up to an additive epsilon and with high probability, pack learning-ish. So what's the challenge here? Talk about single item, for example. Bayesian optimization is completely solved by Meyerson. Naive approach would be construct the uniform distribution over the samples, do Meyerson's optimization for that. You get an auction, output that. And the problem here, a potential problem here, like with many other learning settings, is overfitting. Possibly a mechanism tailored for a noisy version of the true underlying distribution could conceivably perform very poorly on the true distribution. And for this reason, revenue maximization from samples is ubiquitously seen as the next step beyond Bayesian revenue maximization. So this kind of a two-step paradigm has emerged. First of all, understand the structure of good revenue auctions, do Bayesian revenue maximization. Second of all, use structural insights from these optimal auctions to find a low dimension set of good auctions. And we know from statistical learning that if we optimize over a low dimension set for whatever your favorite definition of dimensionality is, we're not going to get any overfitting. And really, the literature has progressed like this. For a single item, Meyerson tells us how to do exact revenue maximization. And then there's a line of work that uses the structural insights of Meyerson to solve from samples in an increasingly general settings. The GN is a stock paper from 2017 with Noam that I won't get a chance to talk about today. So for multiple items, if you want up to constant revenue, There's a beautiful line of work that gives very structured auctions that get you revenue up to a constant. And then there's a beautiful line of follow-up works that use the structural insights from these papers to get you up to constant from samples instead. And what about up to epsilon? As we've said so far, we know some stuff about the menu size. We have no idea what the structure of up to epsilon optimal auctions is in a Bayesian multi-item setting. So it won't surprise you that this last box was left quite in solitude, because why bother when the Bayesian case is still open? Nonetheless, the last result I'm going to tell you about today is a positive result for this box, even though I have nothing new to tell you about the box on its left. So this is work with Matt Weinberg that appeared in the last Fox. So here's the main result. When there's only one buyer, for every epsilon and delta, the sample complexity of learning with probability 1 minus delta, a truthful n-item auction that maximizes revenue among all such auctions up to an additive epsilon is polynomial in the parameter of the problem. I'd like to emphasize that this is for a computationally unbounded seller, so this is an information theoretic result. So it only says that if you have a lot of computational power, so many samples contain within them enough information. This should be compared to a result of Durmi et al. That says that for correlated distributions, even for additive valuations, this cannot be done. This is actually a corollary of a more general result that we have that says that even for multiple buyers, for every epsilon and delta, if you want to learn with high probability an epsilon truthful auction, meaning that by manipulating you could get at most a single cent more, say, then the sample complexity is still polynomial. 2 words about this proof before we start wrapping up. The proof assumes nothing regarding the structure or dimensionality of optimal or even approximately optimal auctions. So this completely sidesteps the 2-step paradigm that's been prevalent in the literature so far. It holds for additive valuations, but even far beyond. Many natural subadditive, even super additive valuations, even with externalities that usually kill revenue maximization. And very elementary tool. None of us is very much a learning person. No heavy tools from statistical learning. And I hope I've managed to tickle your interest. And I'd like to invite you to a talk I'm giving about this result on Friday in the Informs workshop at 5:20. So starting to wrap up. I've talked to you about various aspects of complexity and simplicity in revenue maximizing auctions, the pricing mechanisms. Yeah, sure. Yeah. The same type of motivating questions are applicable to other settings. For example, I've worked a lot on school choice. You can ask questions about the communication complexity. How does it scale? Strategic complexity for various definitions of complexity, less numeric ones. Manipulation complexity, how hard it is to compute a manipulation. How complex is the manipulation? Complexity of preference elicitation. I talked about this yesterday. And last slide, high-level takeaways. I'd like to talk to the non-computer scientists in the audience for 1 minute. Everyone who's a computer scientist in the audience is going to agree that this was a CS talk. Why is this not purely an economics talk? I have not mentioned one result that relates to computation. And really, the thing is that talking about approximations, talking about complexity, is at the basis of CS thinking. So the interface between theoretical economics and theoretical CS goes far beyond algorithms. There are many fundamental notions of complexity that await research in game theory economics. And experience shows that very diverse theoretical tools are going to be needed to crack these questions. So thank you so much. I'd like to thank my advisors and all of the great people who have had the honor of working with throughout my PhD studies. These are everyone who I have a manuscript with from that time. So thank you so much for listening.
All right. I think, Peter, why don't you go ahead and set up so we can stay on schedule.
Mm-hmm.
Maybe there's time for one question while they switch laptops.
So either I was very clear or extremely unclear.
Well, you said quite a lot, Yannai, I think. So one thing I forgot to say at the very beginning of the session is that, as Nicole mentioned yesterday, all the awards will be presented at the business meeting this evening, which is at 5:15. I hope you'll come and congratulate all the award winners again. So let's thank Yannai one more time.
Thank you so much.